So once again, very good morning to all of you. Thank you for joining the session. Myself, Anil Sharma from Impulse Technology. So this session will cover up about the different application on perovskite, organic thin film, tandem, solar cells, as well as LEDs applications. We will try to build in front of you what type of different applications, how the software can help you in your research goals. So this session, as I told you, it will cover up the training session from my side completely, where I will show you the live training on the software part from scratch, how you can create different solar cells, how you can optimize and build your final analysis of any semiconductor devices. So first of all, I want to represent about this Fluxim, which you can see on the screen. Fluxim, that is a Switzerland-based company, and Impulse Technology. I'm from Impulse Technology. We, as an Indian representative of this Fluxim, that is Switzerland-based company. So the two countries are involved. One is called Fluxim from Switzerland, Impulse Technology from Delhi, Gurgaon. So let's discuss about the product that is called SETFOS. The SETFOS is the product name that we will discuss, and this product will help you to achieve your goals in your research fields. If I talk about my parent company, the developer of the tool that is called Fluxim, it is a Switzerland-based company which provides the softwares as well as hardwares, means simulation software and characterization equipments, because they are working on theoretical, simulation, and experimental, and they are developing their in-house product in their research lab. And the software and hardwares, majorly they focus on the organic LED, display lighting, light emitting, light absorbing, solar cells related product, to concentrate on the industrial parts as well as academic institute and R&D research lab also built by it. So the company, the product whatever developing the software and hardware, the majorly it concentrate on the optoelectronic semiconducting device. It could be the OLED, it could be the solar cells. The company was started their journey from the computational physics at Zurich University of Applied Science. In 2006, the company are developing around 18-20 years their product. Beat Rustler as the founder of the company. Now, if we talk about after the company overview, if we talk about the product that is called SETFOS and Laos, you can see this first product is called SETFOS. That is called semiconducting thin film optics simulation software, and allows for large area devices, large area PV module, AMOLED for large application beyond the cell. Beyond the cell, if you want to work on, then this Laos would be required. We majorly concentrate on the SETFOS part today because it is developed for solar cells and LED, for cells applications and LED applications. And apart from that, the since company not only developing the simulation tool, they are developing the equipment for the characterizations. Let's suppose you want to characterize your sample of your solar cells. So there is product called PIOS, Philos, Litos, like these all are measurement equipment which can characterize the electrical optical properties, electroluminance, photoluminance, that Philos is there for stability analysis, Litos light is there, and some other integrated optical parameter characterization, model validation. The company are developing their portfolio in different domains. Now, today's agenda, if we talk about that, majorly concentrate on the SETFOS software. So SETFOS stands for Semiconducting Thin Film Optics Simulation Software. Not only optical, it will started their journey from the optical part, but now they are also able to calculate the electrical calculations as well. So optoelectrical property can be calculated. Now this SETFOS is a very powerful and CPU efficient one-dimensional solar cells and LED simulation software for global optoelectronics thin film based applications. So majorly you can model the structure in our user interface There could be many advantages of this tool will be there. I will present you in the live coming slides, where it can also simulate the LED application, tandem, thin film, unlimited layers. You can optimize your structures based on different parameters. If any parameter is unknown, you can put the minimum value, maximum value, and you can optimize the material parameter, your device efficiency, and you can achieve the maximum efficiency based on different optimizations, including the quantum dot and perovskites. Now, the main particular fields, many people have registered their application in our meeting link. So I would like to tell you, this SETFOS is specifically designed for organic application, inorganic, perovskite, tandem, thin film, heterojunctions, heterostructures, thin film solar cells, dye-sensitized organic photodetectors, quantum dot, organic LED, white LED, tandem LED, blue LED, high fluorescent LEDs, and many more optoelectronics domains. For DFT calculations, nanomaterial application, we have a separate tool that is called Nano Decal and Rescue, which we have presented similar kind of training in last session in July. So this is based on one-dimensional depth diffusion calculations. Now, since it is a commercial software, so software is divided in module. There are 4 modules in the tool. Since it can calculate the optical property, electrical property, emissive property, and some interference calculations. So for SETFOS is divided in module. One is called absorption module. Second one is called depth diffusion module. And next one is called advanced optics module and emission modules. These are 4 modules in the software. And whatever, let's suppose someone works on optical calculations of their material. How much the photocurrent is, how much is the short circuit current, or how much light will get absorbed. Only the optical calculations. Then absorption module will be sufficient, where you can calculate the optical properties. So this absorption module is required for optical analysis, where the depth diffusion module is required for electrical property calculations. Let's suppose you want to calculate the IV characteristics, band diagrams, some emissive properties, or some other electronic and electrical property calculation, then this depth diffusion module will be required. So absorption module for optical calculation, depth diffusion module will be for electrical calculations. And both module can calculate optoelectrical properties, optical and electrical, or optoelectrical at a time. For advanced optics module is there. Let's suppose you want to work on non-flat structure, some textured layers, some interference, or some quantum dot, some nanoparticle effects, some ray tracing analysis. Then this advanced optics module will be required, which is common. Depth diffusion advanced optics will be common for LED and photovoltaic. Emission module will be required for emitting devices, that is called LED application. So either one module or 2 module may be sufficient for photovoltaic application, and dependent on the validity. 1 year validity, 3 year validity, 5 year subscription validity of the software. We have different packages. So this is all about the module. The software is divided into whatever module may be required. Sorry. You may be required the absorption module or depth diffusion module. So accordingly, you can plan. Now, this is since a presentation session is very small. That's why I want to concentrate the main point. So if we talk about the advantage of the software, what could be the major advantage of the software? The advantage is called there is completely a sophisticated user interface. It is not having only the coding part. The coding is also optional part, but the user interface is also given, where people will not have to learn the C, Python, or any other language will not be compulsory. But if you know the coding, then you can also implement as an advantage. Results can be generated in single click, where whatever the analysis you want to click, it can generate in all standard format. Ion transport is one of the key parameters, where anions and cations, the perovskite, tandem, thin film, even majorly in the perovskite part, Apart from charge transport can be done in many other tools, but the ion transport along with charge transport will not be possible in escape bundy or any other softwares. That's why it support the ion charge transport calculations. Some with hysteresis effect, Windows Linux platform is supported, Mac OS is also supported. Some roughness parameter, AFM, BSDF, experimental data you can import. DC simulations can be done by any other tool, but DC, AC, transients, small signal analysis, and impedance analysis. So DC, AC, transients, impedance, and small signal analysis that can be performed by using the SETFOS. Unlimited number of layers are there in your semiconducting devices. Let's suppose you want to simulate one solar cell where multi-junctions are there, multiple layers are there, more than 10 layers, 8 layers, 20 layers, 30 layers, 40 layers. You have a big structures. Then the software can easily handle that complex number of layers structures, but open source cannot do that. So unlimited semiconducting layers with tandem devices. You can calculate the optical properties of particular material. Total device analysis can be performed. You can optimize the multiple parameter at a time. Let's suppose you have an unknown the active layer thickness. You don't know the work function. You don't know the homo value of particular material. So the parameter, whatever it is unknown for you, you can optimize that parameter, and then you can use that particular material parameter to your device simulations. Since software is commercial, where, as you know, in this emerging field, there are new updates are coming. New technology are changing rapidly. So new features are coming where you can get the technical supports, and also you will get some latest features update. Some impact ionization models are there, Auger recombination, SRH recombination, bimolecular recombination, simplified SRH recombinations. Many other model will be there, including the quantum dot with nanoparticle effects. Multiple parameters you can sweep and optimize. Emission module will be there, CIE color diagram will be there, radiance, ELPL data it can also calculate, and reflectance, transmittance, state of art mobility models are there. In open source software, there may be a constant mobility model where you can define the electron mobility and hole mobility. That could be a constant one. But the mobility can be dependent on the wavelength. It can be dependent on the temperature. So dependent on the different parameter, if you are changing the mobility, and due to that mobility, the efficiency of your device may be changed. So this SETFOS support state-of-art mobility model where you can use different time-dependent, temperature-dependent, wavelength-dependent mobility that can enhance your characteristics of your material or device analysis. Few of the advantage I have shown you on the screen. Many more will be there. Once you will have this software in your hand, then you will find the commercial tool have a lot of advantages as compared to the open source one. But different tool we have different applications. This is all about a brief summary about the SETFOS. If somebody want to go beyond that, if you want to work, let's suppose on PB module, the interconnected cells, then another software we have, that is two independent softwares. The company has developed two independent software. One is called SETFOS, that is for cells applications, LEDs application, for small area devices. When you go for large area devices, so this is LAO software, large area organic semiconducting devices, where you can also design, optimize simulations, electrical, optical, thermal calculations, and you can minimize your losses. Whenever you are simulating the solar cells, there may be cause that the electrical losses are there, heating losses are there. It could be due to the geometry of your devices, or optical losses will be there. Your device may be overheating. That's why the losses are happening. So that to overcome that kind of losses, the company have developed this LAO software. When you go increase your cell dimensions. Okay. So that's why this electrical module, this LAO is also divided in 3 modules. SETFOS was divided in 4 modules. This LAO is divided in 3 modules. So electrical module where you can minimize or optimize the electrode design structures, the geometry of your solar cells, Let's suppose some mesh may be different tetragonal, hexagonals. So you can reduce your losses, electrical losses, non-ideal effect, pixel crosstalk in RGB, or heating losses, two-way interaction between the heat generation and electrical property of semiconducting devices, temperature distributions in solar cell and OLED, non-ideal IV characteristics, electrothermal couplings. So the thermal module will be there. Similarly, the optical module will be there for 3D ray tracing algorithm, 3D optical element, and optical crosstalk in OLED. The SETFOS software can also be coupled with LAOS. Let's suppose you have simulated your IV characteristics by using SETFOS, and you want to couple, you want to integrate the SETFOS with LAOS, then both two can also be integrated. So results of one-dimensional IV characteristics can be imported in the LAOS softwares. That is big advantage. Either you may be using different software that you may got the IV characteristics. That IV characteristics you can import here in the LAOS, and then you can change. You can visualize that how the losses are happening, how to minimize that losses. So for large area application, this LAOS will be required. So our company, this Impulse Technology, which providing different tool in this scientific community. So as I introduced about SETFOS and LAOS, and this equipment are there for optical characterization, electrical characterization. BIOS is there for around 15 analysis can be done with single click. All electrical, optical, IV measurement, impedance measurement, transients measurements, and other optical and electrical characteristics, BIOS is there. For electroluminance, photoluminance, PL and PL data, this PHELOS is there. For degradation analysis, this LITOS is there. And for 56 channel perovskite stability analysis, LITOS light is there. So we do provide the optoelectronics, semiconducting device simulation software and characterization equipment, along with the atomistics material and device DFT calculation, that is called nano decay and rescue. For density function theory, non-equilibrium green functions, NEGF quantum transport calculations. This is all about the particular different product that we are offering. It is a current customer list of SETFOS, where IIT Madras, IIT BHU, NIT Karnataka, Manet Gopal, Srinagar, Guwahati, Allahabad, Chandigarh, Kerala, Roorkee, Behrampur, SRM, Jawaharlal Nehru Center, Bengaluru, and Marsidanand University, Rohtak. These are the current customers of SETFOS, which we are using in India. This is all about the particular presentation. I would like to go for the live session on the software part. Before going that, I want to show you more details about the product. So you can visit this website in your browser, fluxim.com. Fluxim.com, which is the main parent company name, where SETFOS, LAOS, BIOS, PHELOS. You can click on this particular website and find more deeper insight, deep information about different portfolio that the company are offering in India. So I request to the participant, you can visit later on this fluxim.com websites. And for Nano Academic, you can visit this nanoacademic.com. These are two major partners that we are supplying in our portfolio, different nanomaterial and nano device tools. We can technically satisfy different product according to your needs. Now let's go to the main part, that is called the demonstration on the software, how the software look like, how you can model different solar cells, how you can manipulate the structures and visualize the results of your devices. So let's start the session on the demonstration. So I want to share my software screen. This is SETFOS 5.5, is the latest version. So I click on run as an administrator to provide full privileges to the softwares. Now this is a user interface of software, which is opened here. Now whatever new features are coming, new updates are coming, it will show on top of a screen. So these are current features which updated the new trapping models are implemented in the current versions. I want to close this window, new feature window. Would like to show you the main screen of the software. Now this is the main user interface of software. For the help purpose, if you want to see the manual, there is a help option is there. On the user interface, you can find the manual and tutorials. So those who are beginner and how you will start with the software capability, then the manual is provided during the installation of software and tutorial is also provided. Manual will give you the insight about how you can start your journey with the software. This tutorial will provide how you can create your solar cell from scratch, and this manual will provide you the background informations. Background information in the sense what models are there, what equations are there, on what algorithm, on what physics the software are developed. So that information can be found from the manual part, and tutorial will give you the insight about the modeling the structure from the scratch. Now let's start the session from the beginning. So I want to create a new project here. To create a new project, you click on file options. I would like to ask you, am I audible to all the participants properly?
Yes, sir. Yes, sir.
Okay.
Yes, sir.
Yes, sir. Yes, sir.
Yes, sir. Yes, sir.
Thank you for confirmations. I would like to continue now my sessions. So I click on this file section and click on new button. Once I click on new button, my this structure, default structure will be opened since I'm going to start from scratch. So by default, surrounding unnamed substrate, these has been created. Now I want to create my structures. So I want to create my structure. Here there is surrounding is there. I can mention my surrounding will be as an example top, air on the top side, and then I want to give the name of the new project. My surrounding air is there on the top. Then I will go to the next new material. Let's suppose I want to define as a glass substrate. So I want to make my first, let's suppose solar cell example. So basically in this particular things, I will perform how to perform the optical solar cell calculation. Then we'll go for the electrical one. So I taken this as a 100 nanometer as example. Then this is my third layer. I want to rename this layer. I want to give as an example ITO. Then since I want to add more layers, so to add the layer, I will click on this add button. And I want to define this new layer name that is called, let's say example, P dot. And next layer I want to add, to click on this, I click on this plus sign. Then I will change this layer name. As an example, I want to take P3HT, PCBM. Then again I click on this next layer. I want to take as an example, aluminum. And again I want to take air on my bottom side. There is no meaning of thickness of air. So I can rename air on the top and bottom. This is my structures, where I can define the thickness is equal to 0, glass is equal to 100 nanometer. I take, let's suppose, 125 of ITO layer, P dot layer. I want to take thickness, I want to edit it and want to change this thickness of this layer. Similarly, I want to define the aluminum thickness as an example, 500. And if you want to take in any other unit, you can visualize here. The nanometer is there, micrometer is there, millimeter is there, wavelength dependent. Whatever the unit you want to take, if you want to take in micrometer, you can take micrometer. If you want to take millimeter, you can take millimeter. It's up to you. The software has given the functionality. The user can use the thickness value and their unit according to their needs. So I taken this example. So basically, I started the journey by clicking on file option, then new option, and then I added particular layer by click on this add sign, add layer, and the thickness has been added. The first layer is glass layer, where the thickness is unimportant because it will treat as an incoherent and transparent. So I can mention it is incoherent layer. I can activate this checkbox as incoherent and it will be a transparent layers. Then the cell comprises of ITO with a thickness of 125 nanometer, P dot with a thickness of 50 nanometer, P3HT with a thickness of 100 nanometer, and finally the aluminum with a thickness of 500 nanometers. Now, since each layers, the name I have mentioned and their thickness I have mentioned. Now we have to define the refractive index of each layers. The optical refractive index NK data need to be mentioned. So the air, glass, ITO, P dot, P3HT, PCBM, aluminum, and air. Each layer thickness refractive index I have to mention it. So I will mention this glass layer refractive index, which
Sir, voice is not.
Hello.
Clear.
Am I audible? Am I?
Yes, sir, you are audible.
Okay.
So we have some questions.
I will take your questions after 12:30. So I request, since there are so many participants are there, so one by one I will take after 12:30 your query. In the meantime, if there are any issues related to my voice or the slides, then you should please interrupt me, because if I will take the questions, then it will be definitely we do not have that much of time, because I will take a general question. One to one, we can have a more sessions. Now I want to share my screen again. So I hope I'm audible to all the participants properly. Can you please clarify?
There's no
Okay.
problem. Yes, sir, you are audible.
Thank you very much. So those participants have any issues, kindly check at their hand maybe. If major participants have an issue, kindly please interrupt me. So I have taken this structure, this particular structure. Now I would like to go to the main refractive index part, where I will assign the refractive index property of each layers. So this glass layer, I click on this glass layer and define the refractive index is equal to 1.5. So n equal to 1.5. And air, I will define the refractive index equal to 1.0 for air on the top and bottom sides. Now the next ITO layer is there, P dot layer is there, P3HT, PCBM, aluminum. Each 4 layer refractive index need to be assigned. So I click on this refractive index tab and choose the file tabulated NK value. So I pick this option and click on the import button. I want to import the refractive index from my library, from my database. But if someone have already their refractive index, it is possible where you can add your own refractive index in our database, or you can also use your own refractive index here. I want to show you the library. This is my library of the material. Many refractive index data is given in this particular database. Since there are a lot of materials are given in our library, so all material refractive index are given here. Whatever refractive index according to your particular material you want to work on it, you can choose from there. So I want to choose here from ITO. So I will select the ITO.nk file. .nk is the extension of real and imaginary part of refractive index. I am importing from my library, but if you want to define your own refractive index, the software have that functionality where you can customize, you can optimize, you can modify the existing value, or you can create from beginning. You can new material can also be created, but it is simply a notepad file where the first column you can define the wavelength, second column you can define the real part, and third column you can define the imaginary parts. So the refractive index I have assigned for the ITO from my library. Similarly, the P dot layer, I will click on the P dot layer. The refractive index for this P dot ITO, P3HT, PCBM is not constant. It is dependent on the wavelength. So I am choosing the material refractive index from my library. But if user want to define their own, I can ensure you it is possible. The customized material can also be uploaded in our library. So let's select this P dot refractive index. P dot, this particular 3 material are given, 4 material are given for P dot refractive index. I have choose one of them. Then I click on this P3HT PCBM, click on file option and click on import option and select P3HT PCBM.nk file. .nk is the refractive index and .em is the electrical semiconducting materials. So I am assigning the refractive index with each layer name and click on this, file tabulated NK value, click on import, and this is aluminum.nk. You can open it here. Now each material refractive index has been assigned. Each material refractive index I have mentioned. So in solar cell, the top layer and bottom layer representing the surround medium, it must be the transparent layer. So it will be the transparent medium and as a incoherent. The convention for the direction of light incoming in SETFOS, the light is always arriving from the top. So light will arrive from the top, glass ITO layer. In case the current structure, the incoming direction is from the glass to the active layer. So this will be the active layer P dot ITO. So this is also the reference direction for calculation of the reflectance and transmittance of thin film structures. Now I want to set glass as an incoherent and transparent. Now if I choose the layer thickness more than 500 nanometer, then the calculation point should be reduced. It should not be more than 100 here in delta discretization points. Now I want to run the calculations. So for this glass layer, let's suppose I want to define this thickness 0.5. We can also change we can define this discretization point is equal to 100. It specifies the spatial discretization in terms of distance between two discretization points or number of elements in which the layer is divided. So now I want to run the simulations. So I can define the layer name. Let's suppose solar and sun. Training is my project name. So I mention the name of project and click on run button. Now once I run the calculations, so I have run the simulation. Then we can go to this part and we can see our reflectance, stack contributions, and transmittance analysis. These are few characteristics which is plotted. So if I want to add, I need to add the absorption module to fall the light in our device. So as I told in the presentation, the software is divided in 4 modules: absorption, diffusion, emission, and advanced optics. So initially, to perform the optical calculation, I have to enable the absorption module. So that I have enabled this absorption setting. Once I enable this absorption setting, I can go to this absorption module. I can define the wavelength. Whatever, let's suppose you want to apply the wavelength from 380 to 1100 nanometer. And this is an illumination spectrum that is called sun spectrum, AM0, AM1.5, global spectrum, location and time specific spectrum. Realistic spectrum can also be used. So if I will choose here, you can see these are different spectrum file given in our library where spectral shifting is possible. You can use different spectrum, AM1.5, AM0, direct spectrum, ETR spectrum, or any spectrum. If you have the wavelength and intensity, you can use that. Let's suppose I want to use this AM1.5. It is used here. This is the total wavelength in the red region, and this blue region is the wavelength that we are applying from 380 nanometer to 1100 nanometer. So this particular wavelength range, we are putting the sunlight. Now I want to run the calculation for optical analysis. So I run the job. You can find these characteristics are there. Now I want to sweep the value of this P3HD PCBM. So I click on the sweep setting value. If any active layer thickness you want to sweep it, I can sweep this P3HD PCBM with a thickness of let's suppose 365 nanometer, 375 as an example. You want to sweep the thickness value from 650 nanometer with a step size of 10 increment. And then I can run the calculations. So simulation is done. You can see this photo current calculated. Photo current value is there for this particular P3HT PCBM on the top one. Then different material. The material reference is there. Red one is called glass ICS. Red one is called glass short circuit current. This ideal is called this blue one. This P dot is called this green one. This P3HT PCBM is called and this L this one here. This is called photocurrent, which is calculated by using the software. If you want to see the edge of 10, particular layer wise edge of 10, that which layer will get more edge of 10. Reflectance in terms of visualized graph. So this is the potential visualized graph there. Analysis and transmittance characteristics. If variation of the thickness of PCB, how the characteristics are that will form here, visualized on the right side. The second type is called coding. Those who are preferring to write the coding, then the code will automatically generate. This is a medical half code value here that can be calculated from here. Hello?
Your voice is breaking.
Your voice is breaking, sir.
Hello, am I audible?
Yes, sir.
Okay, I'm sharing my screen again. Can you see my screen?
Yes, sir.
Okay, perfect. So let's continue the session. Now I want to make the device formation for this particular structure. So my first electronic solar cell formation, we have to mention that which layer will be semiconducting layer and which layer will be the electrical layers. So I want to use this P3HT PCBM as a semiconducting. For that, to make the semiconducting layer, I have to enable the dip to diffusion modules because it will help for the electrical property calculations. So this is my P3HT PCBM, which I can set as the semiconducting layers. Then I can go my next coming layer, P dot and aluminum. So I can define this P3HT PCBM semiconducting property. So once I enable this semiconducting checkbox, I can find this tab has been enabled. If I disable this semiconducting checkbox, the semiconducting tab will be disabled. So if I click on it, it will enable it. If I click on it, it will disable it. Now I have to import this P3HT PCBM from my library, or I can put it my value in my these different tabs. I want to hide for the time being this right structure. So either you can put your value in this particular charge transport, where you can see the HUMO value can be mentioned, LUMO value can be mentioned. So HUMO value can be mentioned, LUMO value can be mentioned. 1 minute, I can record the session. So HUMO value will be here, and this is for LUMO value. Either I can mention the value here, the semiconducting property in this particular checkbox, where energy levels are there, density of states are there, dielectric constant value, epsilon is there. If I want to add this P3HT PCBM, which is selected layer right now, if I want to add any doping, acceptor type doping, I have to add the checkbox. I have to add this doping, donor type doping. So we need to activate that particular checkbox and mention the concentrations. And then go beyond. If I will go down, I can find the mobility model. Usually in some software, maybe a constant mobility model are supported, where you can define the electron and hole mobility. That is constant. But the efficiency is not totally dependent on constant. The mobility is dependent on the wavelength also. Sometimes it dependent on the temperature dependent, field dependent, extended Gaussian disordered, correlated disordered. These are state of art mobility model is implemented. So the efficiency of your output may be influenced based on this different state of art mobility. So constant is one of them, but other parameters need to also be research on that. That's why the state of art mobility model are there, some doping concentrations are there, acceptor doping, donor doping, energy levels, density of state, dielectric constant. These are all charge transport parameters. So either user can put the value. If you have known some value, you can directly place your input HUMO and other property here. Either you can put in the checkbox, or you can simply create a notepad file and then convert that notepad file in .em extensions. As you can see, my library for semiconducting material. This is my library given in our database for semiconducting material apart from the optical material. In few minutes ago, I showed you the refractive index NK data. That is optical data. But you also need to use the semiconducting material, electrical material. So these are certain material EM file given in our library. It is simply a notepad file where user can put your value in notepad and you simply convert in .em extensions. So this P3HT PCBM.em I want to take from my library. Multiple options of P3HT PCBM given in the combinations. So whatever you want to use for trap, recombinations and all those things, you can select it. All parameter will automatically fill in these particular checkbox from the imported files. So this value, whatever it is coming, that is imported from the library material, which I have imported right now. If somebody want to work on LED application, then Exciton step need to be enabled, where recombinations, radiative, non-radiative diffusion, generation, annihilations, TADF, thermally activated dual fluorescence, energy transfer. Then this excitons need to be enabled to enable the excitons in LEDs applications. Then either similarly, you have to fill your input by activating particular checkbox and then mention the value. If you unknown, the value is not given to you, then the optimization will be there. Then software can help you to find the optimal value with set by giving an input minimum and maximum, and then software will perform from minimum to maximum and will give you the peak value of particular material input. Similarly, the traps is also need to be enabled. If you want to capture the electron hole capture rate, you have to enable the trapping. You can trap the electrons. So trap type is there. Either you can use acceptor type, electron trap, hole trap, or amphoteric trap, Sans-Socle traps. These are multiple traps. Type is there. Based on the type of trap, you have to mention the trap density, either constant or it will be a dependent on the parameter. Energy distributions is there, exponential, Gaussian, direct, or different trap energy is there. Capture rate is there, electron capture rate, hole capture rates. Either it will take a default value, constant value, or temperature dependence. So trap parameter also need to be enabled when you want to get more enhanced output of your devices. If you will go for this next tab after the trap, that is called mobile ions. It is called anions and cations, where you can define the anions and cations density. So ions can be associated with the mobility. So anions are there. You can assign the constant mobility model, static mobility, field dependent, temperature dependent. These are different mobility model. You can use that particular mobility model. So you can use different ions, associate the ions with the mobility, because ions are the play a major important role, specifically the perovskite application, and define their minimum density up to maximum infinite density. You can define for the anions and cations. Then go to the recombination tab, where it will recombine the electron and holes. You can see the recombination by using the Langevin, Auger, bimolecular, simplified. If I want to use a Langevin recombination, you can click on this add button. You can use not only Auger, you can use the Langevin recombination as well as the Auger recombination, as well as the bimolecular recombination, or you can use the other simplified SRH. So 4 recombination model can be used at a time. So this recombination parameter, multiple recombination model will not be supported in other tools. So you can define their SRH lifetime for electron and hole and trap energy offset parameters. So you can add or delete. Similarly, if you go down, there is an option called enable impact ionizations. So China with impact ionization model is there, and you can use the China with model, China with linear model, and Thornberg models are there. So based on different models, you can use the input parameter for impact ionizations, so that you can see how the behavior by enabling this particular impact ionization on your device characteristics. So these are certain things which will not be found in any other tool. I believe that it will help you to boost your efficiency of your device characteristics. Now this is particular feature of your particular semiconducting tab. I want to import this P3HC PCBM from my library, so I selected and click on open it. Now all the parameter whatever I have to mention, it is taken from my library. Now I have to mention which layer as a semiconducting. So I can mention as a electrode as a P dot as a electrode, aluminum as a back electrodes. And the work function of the electrode also need to be mentioned. The work function could be ohmic type, it could be a thermionic organic type, or inorganic types. So the type of work function you can use here. So whatever the value of your work function, you have to mention the boundary condition work function, electron density or hole density. This is where we are forming the device. Once you will done this, the value of electrode work functions, you have to define according to your convenience. Then next go to the drift diffusion module, where absorption for optical, drift diffusion for electrical. So optical, electrical can be performed at a time. So to run the, to apply some biasing, we have to apply the voltage. So I can apply here the voltage biasing. So I click on this plus sign to add the value. I want to deselect this P3HT PCBM so that it will not enable it. I want to apply the voltage biasing. So I go to this option and select the voltage here. Linearly or other different options are there. Random value or particular value you want to apply. So let's suppose from -1 volt to plus 1 volt with a step size of 0.1. Increment 0.1 increment, you want to apply the voltage biasing. So -1, -0.9, -0.8, -0.7. It will apply up to 1 volt with a 0.1 increments. And then I will click on the run button. And we'll see the device IV characteristics. Now, since we have taken some random value, accordingly the IV is plotted. But when I will take the more accurate value, it will plot the more accurate device your output. Initially, the main purpose, objective of this training to show you the complete features, what features software exist, how this feature software can help you. The research part is not a one-day process where we have to invest your time, and more accurate input parameter need to be given during the input, then you will find the more accurate parameters. But what analysis can be done, the main objective of this, the software can do. This can be plot this device current, power conversion efficiency, power density, band diagram, charge, generation, mobility, recombinations. All these parameters will be there. Since we have applied from negative biasing to positive biasing, how the band diagram will change from negative to positive, from reverse to forward biasing, that visualizations can be seen. To visualize the electrical key figures, there is an option called display key figures. In the display key figures, you can see the fill factor is calculated, GSC is calculated, VOC is calculated, maximum power, power density, maximum power density is calculated. We can also calculate the conversion efficiency. So this is one of the structure which we can follow it. Now I want to take similar example from my library and want to show you some output. So this in the left side, if you see here, these are the left side, few of the example are given. So I can take one of the example. Now this is one of similar kind of structure where the material may be different, but if you see here, the air is there on the top side, glass substrate is taken with 0.5 nanometer thickness, ITO is taken, some top electrode, perovskite C60 and silver. I want to run the calculation for this particular structure. In this left side, you can visualize the layer structure tab and with their energy labels on the bottom sides. So I want to run this simulation. Simulation is started here and calculation is done. If we want to see the IV characteristics, this is the IV value. So this IV value has been calculated. And you can see the peak at which particular value. And if you want to export your data, then you can simply right click and click on the save image. You can click save this data in the form of visible data or in the form of image form. So if you want to save this data, whatever it is calculated, click on save image, click on this PNG, JPG, PDF, SPG. These format, the data can be exported. So let's suppose I want to save in PNG. I can click on this OK button and save this IV data and click on save. On desktop, in the form of my data will be saved in the form of image. So you can see the image data that has been extracted from that particular graph. Similarly, if you want to visualize your data, instead of graph, you want to get the value. Because you are not able to identify the value, then you can right click on this save data visible in the form of text. Let's suppose you want to save this data, IV data, in text format. So this is text format. Excel format can also be data extracted. So I click on this and click on the save button. The IV data has been extracted in the form of value. So voltage is there in the first column, second column current density, J without recombination, third column is with the recombination parameter, fourth column is with the Langevin recombination parameters. So current voltage data, it can have extracted in this particular procedures. Now, if you want to see the display key figure value, this particular structure, the VOC is calculated, the GOC, JSC is calculated, fill factor, you can multiply it by 100 with power density, maximum power density. So around 10% efficiency is getting in this particular structure. By multiplying 100, the efficiency has been calculated. If I talk about the absorption, 380 to 780 nanometer, the wavelength is fall. The sweeping voltage range is minus 0.4, minus 0.2, 0, 0.2, 0.4, 0.6, up to 0.9. These different value, the voltage are applying, and accordingly, the IV characteristics are calculated from this minus 4 to 0.9 value. Now, this is simple structures. If in the same structure, you want to apply, you want to define this ITO as an electrode. So what you can do, you can change this ITO as an electrode. On the bottom side, you can select the silver layer and define as an electrode. Now this C60 and TATM that we can, let's suppose, take as a HTL layer, and this can be take as a ETL layer. So whatever material you want to use, you can define the ETL and HTL, and set this HTL layer as a semiconducting layer, this ETL layer as a semiconducting layers. So this type of structure is possible. Steady states, transient simulations, unlimited layers can be taken in this particular things. This is second type of example which I have modified in my existing library. So in the HTL layer, I will go to the semiconducting type. Either I can mention this particular property of the semiconducting HTL layer, or I can import from my library. If I know the value, I can mention the homologo, dielectric constant, mobility, recombination, traps in these all particular checkbox. but I want to import from my library. So I will go to there. Let's suppose you want to take P3ST PCBM as electrical semiconducting material. I have imported. Similarly, I will go to this ETL layer where I can choose any, let's suppose Spiro emitter you want to take. I selected and taken it. So this is, you can see the energy level in the right side also. The energy level defined here. Layer structure is defined here. The thickness can be taken in this manner. Now, if you want to run the calculation with this particular structure, I can run the job. The simulation is getting starting. Now, simulation is done. You can see here the maximum power conversion efficiency is something calculated. Power density, fill factor is not coming. We will find out the region. GSC is calculated. If you want to see the device IV, if something is missing, then it will calculate. And if you want to see the IV characteristics, this is for IV. From negative biasing to positive biasing, the IV is calculated. So many other parameters are there. Charge density, charge generation, current plot is there. Electrical field, mobility, potential, recombinations. Many things are calculated. If I will go to the optical part, this is for photocurrent value, and spectral part, absorptance, reflectance, stack contributions. Even I will show you some research paper which is published in good journal by many foreign people and as well as some Indian customers. Now, in the same time, if you want to, initially the thing is, I want to show you what type of different combination you can create. So this HTL perovskite, if you want to make some interface, there is an option called add interface. You can add the interface between HTL layer, perovskite layer, and perovskite layer and ETL layer. So this interface can be created. Interface can be enable the Exciton dissociation for this particular interface. So you can define the top, bottom diffusion length, generation efficiency. Hopping interface is there. Some basic attempt frequency, basic frequency or advanced LUMO to LUMO, LUMO to HUMO, HUMO to LUMO, and HUMO to HUMO. This interface could also be possible. You can also enable the electrical field barrier lowering, disable HUMO-LUMO transfer for hopping interface, Fermi direct statistics. So these multiple options are there to enable the interface. Even the interface can be trapped for this particular interface. So you can enable the trapping, SRH recombination for this particular trap and define the interface trap parameter or even the recombination interface parameters. This is interface recombination parameter where user can mention their own value for the interface recombination parameters. So interface between different material is possible and multiple layer structure is possible. I want to take one interface structure here. This is one of kind of structures where ITO, HTL, perovskite, interface, C60, similar structure is there with the sweeping of value, not only a voltage sweeping from 0 to 1.1, the trap density sweeping for N type, trap density sweeping for P type, for top interface and bottom interface. So let it run the same structure which you can visualize this structure. I want to run the job. So simulation is done. If you want to see the IV characteristics, this is current voltage characteristics with a 0 voltage to 1.1 volt. If there is a variation of density, you can see how the concentration of C60 top interface. So if you will define the value of particular concentration, then you will get particular value. If you will vary the value from minimum to maximum, how this current voltage behavior is changing with respect of concentration of C60 interface. So this particular checkbox, if you visualize, not only one particular parameter is changing your IV characteristics, it can change your this value. C60 interface for top. Similarly, the for bottom interface, the IV characteristics, one is for without any recombination. Second one, that is called this blue color. This is called this one graph is for recombinations. I can hide particular graph also. So that minimum graph, whatever you want to see, you can see that particular IV. This is like this pink color graph. What this graph represent? This is SRH recombinations. SRH, including the SRH recombination, high the current voltage for this particular structure, whatever I have shown you. Now, since in this particular structure, you can visualize few layers, but I can tell you the software have lot of potentials, unlimited number of layers you can model in the tool. You can not only perform the steady state calculations, the transients is there, some AC impedance option is there, some transient AC impedance, IMPS and IMBS, intensity modulated photospectroscopy and photocurrent and voltage spectroscopy with a small signal analysis. So steady states, DC, AC, transient and small signal AC impedance analysis is also possible. With unlimited semiconducting layer, state-of-art mobility models, anions and cations. These are few advantage which I show you with the recombination, SRH, auger, bimolecular, simplified, and impact ionizations. If I take any example of this particular transients, then I can go to this. This is another example which I have different material. ITO, some PTAA, some interface. This is perovskite layers. If you want to see the perovskite layer material given in our library, this is all perovskite layers given in the database. But if any material is not present, user can use their own material. User can define, customer can define their input by taking different source, by reading different literatures. You can collect your data and then you can use your data here in the tool, and then you can find how this software can beneficial, more advanced, more accurate as compared to the existing one available in the market. Now this particular structure, here you can see the BCP, C60, different material interface is taken with absorption setting. So not only a standard spectrum that is called AM0, AM1.5, these are two standard spectrum. But since around 200 people are there in this particular webinar, and all of them are sitting on different places. Some of them may be Delhi, Chennai, Bengaluru, Hyderabad, Kolkata, Mumbai. So location and time is specific because latitude and longitude, the sun may have different spectrum on different geographical locations. So that's why there is option called, you can mention your particular latitude, longitude, elevation, particular date, particular time, cloud weather conditions. So these conditions affect your sun, your efficiency based on the sun concentrations. So diffuse light is also there for the scattering module, where particular date and time, the software assumption model is there. There is some theoretical model is also developed and it is mentioned in our manual on what basis the realistic spectrum can be fall on the device, and it can calculate the realistic data based on the realistic spectrum. That's why not only general spectrum, that is AM0, AM1.5, that is standard data. But apart from that, realistic option is also one of them. This is particular perovskite hysteresis with the transients calculations, where steady state solver is there and transient solver is there. Transient solver, steady state solver with auto solver is there, Newton and Gummel plots are there, and you can compute the AC during the transients calculations. Sweeping is there in this particular parameter. The transients electrical signal are sweeping with particular step size in volt per seconds. So let me run this particular structures. So these steady states I already shown you. Single structure, multiple structure, interface structures. We will go beyond that. So let it run the simulation. It is running. It is showing the percentage of calculation running, and it is done. So if you want to see the curve based on the time, this is few transient related analysis. Let's suppose this is the device current with respect to voltage. So IV characteristics with respect to time, multiple graphs. If you see here, this is time dependent graph, and 0.01 volt per second. This red graph is there. 0.1 second. This yellow color graph is there. If you see the difference, at what particular voltage the difference are coming. This is at 0.1 volt per second. We can minimize and maximize the particular value. Let's suppose you want to take this graph, this particular color, a violet color graph. It is at 100,000 volt per seconds. So how the variation will be done? Let's suppose you can select particular graph and you can hide it. And these two graphs which you can visualize, I can hide this one. So this is at what particular voltage? It is at 0.01 volt per seconds. If you want to see at 101, you can unhide this. This one is at 100 volt per seconds. So IV characteristics with the variation of transients, with interface, SRH recombination current, power density, device voltage transients, even spectral analysis, absorptance, layer absorptance. If time variation is there, we can scroll this particular box and time effect can also be visualized. Now, similarly, other example is also there for only optical calculations and only electrical simulations. If you see, this is one of the another example. P dot, P3HT, PCBM, aluminum with ITU. Depth diffusion calculation with the steady states and voltage is sweeping. So let it run the job with simple OPD structures, organic photodiode, and this is IV characteristics. You can see how, at what threshold it will be there. That threshold can be calculated. Even the software can also calculate the responsibility. Also, responsibility of photodetector, that is also possible. If I will go for the other band diagram analysis, this is for band diagram. at negative 2 volt, and from negative voltage biasing to positive voltage biasing. Lumo, there are 4 lines are there. One is called this one, that is called Lumo value. This is called energy reference for N type. This pink one is called for P type energy reference, and this is called Humo value. So Lumo energy reference for N type, P type, and visualized in this particular graphical representations. With electrical field can also be visualized. Electrical field variations. And this is the graphical representations. Similarly, the power density. This is power density graph. I want to take another example for multiple layers. You can see this is one electrode. This is one perovskite layer, second perovskite layer, and third perovskite layer, and bottom electrodes. And absorption setting, where wavelength from 380 to 780 nanometer. This is the light fall, and this is a transient simulations. The transient signals are there and transient solvers are there. If you want to see the solver, this is for transient signals, and let it compute the calculations. Now simulation is running and it's completed. If you want to see your transient profile, this is at 0 second and something microsecond is there. Based on the transient microsecond, how the band diagram at interface is changing. Similarly, Lumo will be there. We can maximize the zoom particular region and we view the output. So absorptance, reflectance, contributions, even optical profile, absorption profile, which layer the light will get more absorbed. So air, top layer, second one is this color, different color extension, glass layer, third layer with different color, that is ITO layer, and this is electrode layer, perovskite 1 layer, perovskite 2, perovskite 3, 4, and 5, with silver and air. Different color with their naming is also mentioned so that you can identify which layer is more light absorbing. And that particular material you can use to make your device. And even if you want to see for impedance related characteristics, we have this one another structure: gold, organic MEH PPB, and calcium. This is simple. The procedure I already explained how you can create such a structure. Right side you can visualize the layer structure, and left side you can see the energy level for this active layer and electrode layers. Depth diffusion, AC impedance. Initially, I performed the DC calculations. DC calculation and transient is already explained. AC simulation is selected in this particular graph. So steady states AC frequency amplitude is mentioned here, and sweeping voltage from negative 10 volt to plus 10 volt with 0.5 increment. So let me run the calculations. And now you can see the electrical impedance characteristics. This is AC impedance with respect to voltage. If we want to see the impedance, this is a voltage graph. This is a Z and Z node, real part and imaginary part of impedance. This is blue one is called imaginary part, red one is called real part of impedance. With respect to voltage, we can extract this data and plot the Nyquist plot from here in Z and Z naught. This is one of them will be Z, and next one will be Z naught. So I can save this visible data, and I can mention the name impedance. And save here this value, and this is my extracted value, where first column is voltage, second column is impedance real part, third column is imaginary part. We can plot this. This is Z naught value, and this is Z dash naught value. We can plot the imaginary and real part, and accordingly we can get the Nyquist plot. So this is all about this particular parameter, conductance. You can also plot the conductance, capacitance, normalized capacitance, susceptance. So one dimensional as well as some AC charge density plot, current plot with the imaginary value also in the graphical and representations. If you want to see the device current, this is for device current by applying the AC amplitude value. So phase, magnitude, charge, recombination, susceptance, capacitance, impedance, electrical, optical. There are range of bunch of lists of analysis are there where the customer can effectively use, and you can plot your outputs. So initially I have presented about SETFOS, a small brief idea about this tool. Since our software, we are not only supplying the software part, not only simulation purpose, because the software results should also be validated with the experimental. So we are also trying to build the experimental lab to many of the organizations in India. So if you want to characterize you are working on experimental part, then we also supply some probe stations. We supply some sample holder for characterizations. So experimental, we have also some setup. So I want to, my colleague Darshan is joined in the meeting from Pandit Deendayal Upadhyay University, Gandhinagar, who will represent some experimental facility that we can supply in your institutions. So I request to the participants, please, half an hour session is assigned to Dr. Darshan from PDPU. He will deliver a small session on experimental facility for same domain, for thin film, material, optical, solar cells. Now in this session, we will cover up basically small about solar cells along with the LEDs applications. So if you are somebody works on amorphous type, PN type solar cell application, then I want to give another structures. This is one of the another structure where multi-crystalline silicon, ZNO, P-type silicon exterior layer, and this is a P-type amorphous silicon, intrinsic amorphous silicons, N-type amorphous silicons, and N-type ETL layers. This is another kind of structure. Right side you can visualize the layer structure tab, and below that there is energy levels. In middle of that, in between that layer, electrode, between top electrode and bottom electrode, there is some semiconducting layers, and each their layer define their semiconducting property in this particular tab, where homolumo are defined, mobility are defined, dielectric constant, recombination, trace, anion cations, all those things are specified. So I want to hide this right side visualizations, layer devices stack, and this is all particular structure. In this particular structure, we have defined the acceptor doping with 3 into 10 to the power 24 per meter cube concentration of acceptor type doping. We can use N-type, P-type, and the mobility models. Similarly, this is N-type on the back side with the donor type concentrations. So acceptor type here, the P-type is there, N-type in this, and in middle of that, there is without any dopant, pin structure is there, P type, N type, and this is intrinsic without any doping in these regions. So this is one of another kind of structure where it's AM 1.5 steady state calculations, and voltage is sweeping from 0 volt to 1 volt with increment of 0.02 steps. So from 0 to 1 volt, 0.02 step size, you can increment the value. You see here, there is only one parameter voltage is sweeping. But it is not like only one parameter you can sweep at a time. You can sweep multiple parameters, 2 parameters at a time, let's suppose wavelength and voltage, and temperature also, thickness also, homolumo also, or any parameter as an input you will give it. That parameter you can sweep and optimize so that you can find the variations, the effect of different parameter in your device results. So single parameter in this particular case is sweeping. So I want to run it, the simulation, both this amorphous pins, solar cell, electrical and optical characteristics. So the simulation is running here. It will show here the percentage, how much calculation percentage done. The software is very fast in running the job. It will take 2 minutes, 5 minutes, 10 minutes, like that. Now this is current voltage characteristics. Okay. Plus biasing, it is at Fermi level, that green one, and this is at top IV characteristics and negative. Accordingly, you can plot how the behavior will come with different trappings analysis. Similarly, this is power conversion efficiency. If you see, click on display key figures, you will find the electrical key main figure value. VOC can be extracted, GSC, fill factor, maximum power density, and maximum power conversion efficiency. You can see different trap recombination current per distributions, trap recombination current per distribution balance, and trapping current per distributions, and these characteristics. If I will go for electrical profiles, this is for Venn diagram. You can zoom particular regions. This is for interface with different materials. Even if you want to import experimental data, this is import button. You can also import your existing data and you can compare your result with the existing ones. If I take, if someone want to get the quantum efficiency, then I want to take another example. You can see P dot as a top electrode, P3HT PCBM, and aluminum. This is as electrode is taken. Single wavelength we are defining here in the absorption setting, depth diffusion steady states calculation, and the wavelength is sweeping linearly from 300 to 800 nanometers. And now we will plot the external quantum efficiency for this particular solar cell structure where P dot, P3HT PCBM, aluminum. Let it run the job. And you can see this is a photocurrent with respect to the wavelength. At what wavelength you will get the maximum photocurrent, and at what wavelength you will get minimum photocurrents. If you talk about the quantum efficiency with respect to wavelength, this is EQE with wavelength analysis. So how the wavelength and IV characteristics, including the power density and other graph, could be possible. Stack contributions and optical profiles, absorptions, which material will get more light absorb, that absorption analysis, absorption rates, we can plot that like that. Now till now I have shown you a few example. This is one of energy yield calculations. So let it run this energy yield calculation where the absorption, the particular date and time the device were simulated, where latitude of particular location, longitude, elevation, date, time, time zone. We can also change the time zone because different time we have different spectrum. So that's why the spectrum realistic condition is given here, and time is sweeping. So let it run this energy yield job calculation. Simulation is running. We can calculate the incident spectra. Incident direct spectrum is called this red one, and this blue one is called the diffuse spectrum. So you can see the direct calculated incident spectra on particular location and diffuse spectrums. This is energy yield with the particular date and time zone. Generated power with day and time, incident intensity, solar angles, many more things are there, including the photocurrent of different material on different time zone. Let's suppose you want to change this time zone, since nowadays the time is uh, August is going on, so we can change it from 2021 to 23 August. So we can make it, let's suppose 10th August. I have taken it, and I can sweep the time reflection also. So the time will be taking with the interval. Sorry, 1 minute. I have to change here as well. Start time and date time. Now you can see according to the date 9th August, 10th August, 11th, 12th, night and morning, evening, that spectrum will plot the different photocurrent, particular realistic value. So I want to say that if you want to calculate some geographical location based analysis, that's why that software have developed their own different functions, and accordingly you can plot the different analysis on different scenario. The different scenario can be created, and accordingly the different data time zone you can see at AM time, PM time, 9 AM, 10 AM. Time based spectrum is very unique in this. Okay. And energy yield calculation is calculated kilowatt hour per meter square, the energy yield calculations. Now if you go for more multi-junction structures, there are few other example is given in the library. MOO3 CY7P C60 interface with this particular things, with the diffusion length is mentioned for the interface, C60 recombinations. So we can also run it and visualize our output. You can see how the device behavior will come. Now if I go for tandem devices, you can see this is one of the tandem interface device where substrate, ITO, P dot, polymer, ZNO, then again P dot, polymer, aluminum, and then air. This is one of kind of structures with tandem IV interface is created. So if I will, you can see this layer structure tab. I want to run the job, and this is the device currents, and this is display main key figure, power conversion, power density, fill factor, BOC, GAC. These all are plotted. So multiple scenarios. It is not restricted to 5 layers, 7 layer, or 8 layers. You can create n number of layers, and you can create multi-junction, 2 junction, 3 junctions, kind of structures. Now I want to show one another example, which is basically around 10 layers are there, 12 layers are there. So if you see here, this is one another complex structure. SNO2, C60, perovskite, nickel oxide, interface, middle ITO, amorphous silicon, intrinsic silicon buffer layer, N-type buffer layer, N-type HTL, bottom ITO. And then once you created, so this structure creation is very simple, that I have presented in first half, that how you can create this from the scratch. By simply you can add n number of layer by clicking on this add button layers. So this add button layer can create so many structure according to your needs. Then go to the absorption setting, where you can select your spectrum either from the that library given a spectrum, or you can also create your spectrum. This .sp extension, that is spectrum file, where you can define your wavelength and intensity. If you want to visualize the spectrum, from where the spectrum data is taken, you can see this spectrum information, where AM 1.5 global spectrum with this NREL. This is source of this spectrum. From there, this data is taken for global tilt AM 1.5 spectral radiation from solar disk plus sky diffusion, diffuse reflected. First wavelength, first column stands for wavelength. Second column represent for intensity. And this graph represent for wavelength versus intensity, the spectrum AM 1.5 global tilt taken from NREL reference. And this 300 to 1200 is the range that we want to do study. So this is green spectrum, and this is total whole spectrum. If I go for diffusion calculations, this is steady state transient impedance. So in this particular structure, we are going to perform the steady states calculations. We can perform not only a recombination. If you want to define the electrical circuits, then you have to enable the electrical circuit with that. Define the series resistance, parallel capacitance, lateral resistance, and attach the circuit with your device. So circuit mix mode simulation can also be done with that. And sweeping is there, where voltage is sweeping with the particular zero voltage with different value of voltage, not linearly. Linearly is not mentioned here. On particular value, we want to run this tandem perovskite silicon electrical characteristics. So the simulation will start here. Since the number of layer has been increased, so it may take few minutes. The simulation may take few minutes because the number of layer has been increased. So within 2-3 minutes maybe, we can expect our simulation will be finished. It is not required high-end workstations. It can also run on normal computers. Many software take 1 day, 2 day, 3 day, but it is not like that. Now simulation is done for this tandem perovskite silicon structures. This is IV characteristics. Okay. This is simplified SRH recombination IV. If you click on this particular graph, this is recombination IV. This pink one is bimolecular. This red one is J without any recombination. And this green one is Langevin recombinations. Some of them are overlapping. So we can visualize each layer recombinations output. And that data can also be exported. So if I want to export this data, save visual data, tandem IV. And if I see this extracted value, you can see first column is voltage, second column is current density without recombination, third column is recombination, fourth one is Langevin recombination, bimolecular, total J trapping, total J recombination with SRH, internal recombinations. So accordingly, this graph has been extracted, which you can use in your publication after once you procure the software. So it is commercial tool. If you want to see the interface SRH current with respect to voltage, this is interface SRH. This is power conversion, it is power density, and see the electrical key figures. Around 28% maximum power conversion efficiency for this tandem device. We have to multiply it by 100. Maximum power density is there, fill factor is there, negative current density and VOC values. If you want to see the electrical profiles, I can click on this Venn diagram. And in the Venn diagram, you can see this is a interface regions. I want to zoom that particular interface region and want to see our electrical Venn diagram. This is Venn diagram. At the interface regions. In which layer it is? The layer name is called C60, perovskite, nickel oxide, middle ITU, amorphous silicon, and amorphous silicon HTL layers. And this is the valence band and conduction band. The band can be plotted like that. Similarly, other plot, if you want to see the charge density, we have to zoom particular regions and see the voltage variation in your any charge density analysis. If you want to see the variation in your voltage, this is the variations. In which layer the maximum variation are affecting your charge density or any analysis. Then it will represent the variation in your Vicing. Similarly, the recombinations are there. So recombination, if you want to see, this is for recombination things. At zero voltage Vicing and other Vicing analysis. So this recombination graph, Langevin, bimolecular, simplified as such. Now let me go to this our next LED session. We can also discuss because the tool is very vast. There are a lot of functions are there, a lot of features are there. And even if I show you the research papers by using this SETFOS, you can go to this Google Scholar and even the websites also. This is fluxim.com and publication websites. So these two links are there where you can find a lot of publications are there. You can scroll down this well, drop down this menu and find all the publication list. If I will check here, SETFOS from India, these are some papers. Perovskite solar cell with the efficiency of 31.51 using SETFOS. Perovskite solar cells simulation. Even if you see here, this is one of the paper which is published by IIT Madras. Dr. Dilip Nair, Dr. Soumya Datre, Soumya Datta and Devdatre, they purchased this software and published on LED application. So very broad range of publication paper which given on website as well as on the Google Scholar. So you can find how the software will be reliable, useful for your upcoming journey of this particular domain. So if I select this perovskite, all the paper will be perovskite shown here. So these are all perovskite papers. If I will see, this is for like triple junction perovskite silicon solar cell with power conversion efficiency 24.4, and many SETFOS paper will be there. If I will mention SETFOS, you can find here pulse operation of perovskite LED, study of role of mobile lines, degradation analysis of perovskite solar cell by short circuit impedance spectroscopy, nickel oxide passivations, SETFOS was used. So these are all publications. You can, there are so many things are there which I cannot explain within this duration of time. Now I would like to perform the main thing. You can watch these information from website can be taken it. If I will go to the next part where I can inform about the little bit LED, then we'll take about your questions. So in this coming time, I want to present to you some standard tasks with the SETFOS step by steps on light emitting diodes. So first of all, I will step by step fully simulate a full functional OLED. So I will go to the new option and new, and the default stack has been added. This is default surrounding, unnamed and substrate. I can add n number of layers by simply click on this add button. If I click one time on add, the new layer will be added. If I click again add button, it will be added. So I can click multiple times on this plus sign. That number of layers will be added in this particular stack. So I can define, and it will reflect in the right side of the layer structure as well. So I can add, delete, duplicate, invert. I can change the layer name and all those things. So this is one information where I can add n number of layers. So to perform an emissive OLED calculation, we need to enable the emission module. In first half, I enabled this absorption module, that is for optical calculation, and diffusion module, that is for electrical calculations. Since for LED, this emission module is required, so I have to click on this emission module, bulb sign, it will enable the emission module. Now we will consider the layer structure tab. This is layer structure tab, and I will define the layer property. SETFOS always calculate the emission spectra outcoupled to top layer of the device structures. So I want to inform you the SETFOS will calculate the emission spectra outcoupled through the top layer of device structure. So we want to calculate the emission spectrum into the glass layers from the top into the glass substrate of an OLED. So we can define this is as a glass substrate and this is air on the top. We can delete it. We can take this glass from the top. And these layer has been added. Now we have to define the name of these layers and define its properties. So I want to define this next layer name that is unnamed. So I have to define each layer name with their thickness. So this layer name, let's suppose I want to take ITO. The next layer I want to take P dot. Then again next layer I want to take polymer. Next layer I want to add it. So I click on this add button. I can add as example calcium. Then again I click on this new layer and click on aluminum. And then again I can define some surrounding back layer. We have to define thickness of this each layers. So we have to, let's suppose thickness of ITO is equal to 10, P dot 10. I want to take 10 nanometer thickness of all the layer except glass and surrounding bottom. Now this particular structure I have taken. The top and bottom layer are taken as a semi-infinite medium. Therefore, the thickness is irrelevant for the top and bottom. And I will define the constant refractive indices of these materials that do not show any dispersions. For a calcium, I will define the refractive index n equal to 0.75 and k equal to 2.2, real part and imaginary part. For a P dot, I want to define n equal to 1.5. I want to take it constant. So for ITO, I want to import the refractive index from my library. I click on this file tabulated NK data, click on import and select this ito.nk file. Similarly for aluminum, I will select this aluminum layer, select the file tabulated NK data and choose aluminum.nk file. And for polymer also, we have to define the refractive index. I will take some polymer refractive index data from my library. User can define their own value. So let me take polymer material, which I can take pfo.nk file. So I have assigned the refractive index for each layers. Now we have to define the emitter layers. Here we will define this polymer layer as an emitter. So if you see, once I enable this emission module bulb sign, this emitter will be enabled. So I will define this polymer as an emitter. And I have to set this layer as emitter. So to define the property of emitting dipole, I will go to this emitter settings. And I have to assign the luminance file with that. So for this polymer, I will assign the luminance PL data, photoluminance data. So some apart from refractive index, optical, electrical spectrum, there is another file present in the library that is called PL, photoluminance data. So I will choose that particular luminance for the polymer. Let's suppose this MEH PPV polymer. I want to use this PL data. So the PL data I have imported. Now this multiple delta distributions, exponential distributions, Gaussian distributions, exciton coupled, absorption coupled, recombination coupled, master equations coupled, these have been enabled. I will select the delta distribution with a position of 0.5 shift. And we can also see the preview of the luminance, the wavelength and intensity graph. This is wavelength and intensity PL data for this polymer layer. Now the SETFOS can display a preview plot of imported luminance file, and we assume that wavelength and intensity value are stored in first and second column. So first one will be the wavelength and second one will be the intensity. We can also modify this tabulated data. Whatever this data it is showing here, I can click on this zoom. First one is wavelength, second one is intensity. If you want to modify, the things can also be modified. That is also possible. So the PL data, you want to use your own PL data, it is also possible apart from the existing one. Now by default, the spectrum will be simulated from 389 nanometer to 789 nanometer range. If I go to this emission setting, you can find 380 to 780 nanometer. This emission spectrum will be simulated. And this atom we can also change it. If you want to change, it can also change according to your convenience. If you want to use different other spectral variable, you can also use that. To model, for the model to work, the emission layer must be transparent in the emitting wavelengths. So we have to set this emitter layer as a transparent. We have to enable this layer as a transparent in the emitting wavelength region. So we have enabled this polymer layer as a transparent layer. Now for optical emissive calculations, it is done. So I want to define the name of project OLED training test and want to run the simulations. So simulation is running. If you want to see here, you can visualize the reflected color, emitted color, intrinsic colors. And this is display key figures where optical value and optoelectrical value can be calculated. So luminous efficacy, current efficiency, luminance, radiance, peak intensity, peak wavelength, and equilambertine. That can be calculated. If I see on the CIE color diagram, this is CIE color diagram where we can plot this blue, green, and red region. Similarly, the excitons, if it is there, it will display dipole. If you want to see the emission spectrum, we can click on this emission and we can visualize this emission spectrum without any polarized, S polarized or P polarized. So this is without any polarization. This is with the S polarization, and same thing, this is for P polarizations. And this is a wavelength range that the spectrum is plotted. Now SETFOS can calculate the outcoupling into the glass layer on top of stack. In order to calculate the outcoupled light into the air, we have to introduce an additional air layer on top of a stack. What I want to say, this SETFOS can calculate the outcoupling into the glass layers on top of stacks. Outcoupling into the glass layer on top of stacks. To calculate the outcoupled light into the air, we have to introduce additional air layer on the top. That's why I want to click on this add button. This unnamed layer has been added, and I will move onto the top. So the air layer I have moved to the top, and define this layer will be as a top layer. Now we have to find the arbitrary thickness. Yes. Am I audible to participants?
Yes, sir. Yes, sir. You are audible.
Thank you for confirmation.
Yes, sir. You
So air layer with arbitrary thickness of 100 nanometer, for example, and the corresponding refractive index I want to set as a 1. The air layer refractive index I have set as a 1. The substrate layer has a thickness of 700 nanometer. So I want to change, let's suppose, the thickness substrate layer, and we have to consider it as an incoherent. So furthermore, we will set the number of discretization points, where I can add this discretization points up to 100, so that it will solve it in that particular manner. I have changed the glass substrate thickness. Now I want to, since I have added the air on the top, so I change the file name as well and want to run the simulations. Now these results are new as compared to the previous one for this emission spectrums. And we can also compare the results with the previous one. This was, there are 2 projects which is created right now. You can see one is called this OLED training test, and this one is called air. So these are two results which is calculated, and you can clearly see the difference. If I want to make it Control C the results and then Control B on the paste. 1 minute. I copy all the curve and let me paste all the curve. And I have copied and pasted the curve from previous one. And accordingly, you can see my results variations. This is copied curve are there and without copy curve. The C+1, this one is curve, which is I have copied, and this is top. So this red one and pink one, that can be compared for the emissions. So two project without including the air and with including the air, I have got the emission spectrum and see the comparison between two. That's why the 4 curve has been included. One is called previous one, copied result, and without copied result, original one. So this is all about how emission spectrum and other optical property can be calculated for optical analysis. We can also perform the electronic OLED calculations, electrical calculations. Now we are going to simulate the device for electronic IB characteristics. So the device which I am going to simulate, that consists of gold electrode, polymer layer, and calcium as a cathodes. So I want to take new project with electrical calculations. I click on file option, and then default stack is generated. I have to add other number of layer. Now I want to define the gold electrode, surrounding, polymer, calcium, and substrate. So the device I am going to simulate gold as a anode, MEH PPB layer, and calcium as a cathode. First of all, I will simulate the pulse operation and analysis the transient current. Afterwards, I will sweep the voltage and calculate the current voltage curve of device, and then we will build the optoelectronic coupled model. Now this is my layer stack. I want to rename this layer. So I want to define my gold as an anode, polymer MEH PPB. Then I will take calcium. And then I can take substrate. So this is my layer name. And I want to define set the thickness to 10 nanometer for gold, 120 nanometer, 110 nanometer, 100 nanometer. This is my thickness. So I have set the thickness correspondingly. So I want to set this MEH PPB layer as a semiconducting. For that purpose, I have to enable this dipped diffusion layer, because ultimately for electrical calculations, dipped diffusion model need to be enabled. So I want to set this layer as a semiconducting and activated the corresponding checkbox. So we have to define the electrical property for this MEH PPB. That's why the semiconducting tab, I have enabled it. Now to set the electrical property of this MEH PPB organic material, I will go to the semiconducting tab and import the semiconducting property. Either I can mention, as I told from the scratch, either I can mention this particular checkbox by filling the HUMO-LUMO, dielectric constant, doping, concentration, mobility, Exciton, trace, recombination, mobile. Either we have to mention it or I can import from my library. So initially I want to take it from my library because this MEHPPB semiconducting material file is given in our database. So I select it and click on open it. So electrical property will be automatically filled it from the file which I am imported. Now I will set this gold as an electrode. Similarly, bottom side calcium, I will set as an electrode. So gold, active layer and calcium. But I want to set this gold layer instead of ohmic injection model. I want to select thermonic type. Thermonic type boundary condition for both the electrodes. And I will set the work function for this calcium, that is called 3.3. And for gold, I want to take, let's suppose, 5.1 electron volt. The energy level diagram display the chosen HUMO-LUMO level for MEHPPB material and corresponding work function for both the electrode. So this energy level, whatever you can see here, display the chosen HUMO-LUMO value. Now, I want to apply the pulse current operations. So we will simulate the transient response to an applied square pulse signals. So that's why I will go to this drifter diffusion settings and I will choose transient instead of steady states. In the transient signal, this step I will define the square voltage signal. We can use participant, please unmute your mic. So we can use voltage, temperature, electrical. I will enable the electrical transients. Steady states is there. And we can apply some voltage. Let's suppose I apply here 0 voltage biasing. I will define the squared signal by 3 constant segments. So I will click on this plus sign. Again, here you can see that I can click on plus sign 3 times, and this is at 0 level with 50 durations. So the first segment I defined 0 with 50 duration microsecond. So the device will stay in the 0 steady states for 50 microseconds before it gets pulsed. And for the second segment, I want to define label to 4 voltage with a duration of 100 microseconds. And for this third segment, I want to define the 0 voltage again on the same phase with a duration of then 50 seconds. So I have applied this pulse durations. This is a transient signal preview pulse. The squared signal is now displayed in this transient signal preview. This is squared signal that I am applying here. It is also possible with the for solar cell as well, not only LED part. The total time of transient simulation is defined by the length of transient signal. So the total signal length is 300 microseconds. Now I will go to this transient solver tab where I will set the numerical setting and define the output time steps. Tolerance, numerical tolerance I can define, and it is already defined to 1 into 10 to the power minus 5 with a time step of export time step to 5 microseconds. I will enable this checkbox. Now I want to run the simulations. So I can define this LED with the transients and click on run button. So simulation is completed. If you want to see the output, this is called device current transient curve. This is device current versus voltage, device voltage transients, power transients, current valence transients. Now for the current voltage curve calculations. For IV curve, I will go to the drift diffusion solver and select the steady states. And then I will click on the sweep setting where I will set the voltage biasing. So I will go there, I will click on voltage and select 2 volt with the 10 volt. 2 volt to 10 volt, voltage sweeping 0 to 1 volt for IV characteristics of this LED. Here I can change the name of project, IB. And now I want to run the simulation. So the simulation is done. I will click on this device current. And you can see the current voltage curve for this LED has been plotted. So individual recombination channel and languid recombinations. This is for recombination, languid recombination, that is hiding on the each other. This one is for languid recombination and individual. This is for individual current with respect to voltage. You can also plot semi-logarithmic. If a semi-logarithmic plot is required, we can activate the log. This is log checkbox where it can plot for the x or y axis. Now after this electrical pulse transients, if you want to go for electronic to optical coupling, we can also perform from electronic to optical coupling. So we will solve the depth diffusion equations and use the calculated exciton distributions as an emission source for the optical light outcoupling. So we will solve the depth diffusion for electronic to optical coupling. We will solve the depth diffusion equations and use the calculated excitons distributions as an emission source for the optical light outcoupling.
क्योंकि इसको निकालने की जरूरत ही नहीं है अपने को। हाँ मतलब इससे है ना।
Now I want to tell you, I want to perform from electronic to optical coupling. So this will solve the depth diffusion equations and use the calculated exciton distribution as an emission source for the optical light outcoupling. So I have to enable for optical light outcoupling. This emission module need to be enabled for emission mode. So I enable this emission module. That's why this emission setting is enabled. To calculate the light outcoupling, we must specify the refractive index of the material. So we have to specify the gold refractive index. I choose the gold one and go to this refractive index tab and select the file tabulated NK value and import the optical refractive index data of this gold layer. So I will choose find out the gold in my database. This is au.nk file is given in the library which I am importing here. Similarly for MEH PPB, I have to import the tabulated NK file. For MEH PPB refractive index, this is mehppb.nk file. So I can choose here, and similarly for the calcium refractive index, I will upload here. So I will find out where this calcium is and then assign that particular NK refractive index data. The corresponding is air with a constant refractive index of 1 and substrate glass. This is substrate as a glass with a constant refractive index of 1.5, and this is as a surrounding air which is called as 1. And we have to set this MEH PPB as an emitter layer. So I will define MEH PPB as a light emitting layer by activating this emitter in the general layer property. Now in this emitter setting, we have to assign the luminance. So I will go to here luminance and choose the luminance files. This is MEH PPB PL data. I can select it and upload it. This is uploaded the luminance spectrum. Now we have to enable the coupling for the excitons. So I will go to this bottom distribution type. Distribution type, multiple options are there for the distribution. Delta, exponential, Gaussian, excitons, absorption, recombination, master equations. So I will select the exciton coupled, and this exciton coupled is done. Status is okay. Now excitons coupled has been done. Now the SETFOS can calculate the exciton distribution as a source for the dipole. All the exciton parameter like diffusion constants, radiative decay rate, etc. are already defined in the electrical material file, which I already choose for this file. So all the semiconducting property which is given here, and that is assigned. You can see this is the exciton, where the diffusion constant, generation efficiency, and all the parameter, basic parameter required, that mentioned here. Now I will go to this diffusion settings and activate the checkbox. The checkbox is there for excitons. It is here. I have enabled this checkbox for the calculation of excitons. Now I want to run the job and give the name of my project. Now simulation is done. If you want to see some different spectral emission, I can go there and click on emission spectrum. So these properties are calculated here, and some other emissive property, some luminous efficacy, and some other band diagram, and all the excitons, internal efficiency, device currents, and optoelectrical properties, device efficiency, EQE, Lambert-Eaton, generated photons, and passive optical analysis. So you can follow the same procedure for LED calculations also. That's why you can get many other analysis. I want to take few examples from our library for the LED, which I have tried to show you from scratch. So if you go in this left side, couple of examples are there already. So I want to go this are example for multiple emitter layer. This is one of the example for full OLED with doped anode, HTL layer, and 2 EML, multiple emitter layers are there. EML1, EML2, electron transport layer, and gold. Layer structure, energy levels, refractive index, all the electrode parameters are mentioned. Emission setting, spectral, and depth diffusion steady states calculations. Let it run the job. Exciton quenching. Now you can see the reflected color, emitted color, intrinsic color with their excitons and their electrical profiles. This is band diagram. If you want to see the emissions, this is emissions also. Normalized emission is also possible. White emission is possible. Absorptance, radiative decay density, radiative dipole density, radiative rate profile, refractive index, and other emissive CIE color diagrams. If you want to see the emitter layer property, I can go to this EML layer. This is semiconducting property. In the charge tab, some charge energy level are mentioned, HOMO-LUMO mentions, dielectric property are mentioned, and mobility. This mobility will not be supported in a common softwares because it is a field dependent mobility. So field temperature, extended Gaussian, extended correlated, disordered type mobility model. Then exciton, single exciton, double exciton, triple excitons, energy transfer, annihilations, triplet, singlet, triplet excitons, radiative decay, generation efficiency, diffusion constants, quenching, polaron, excitons, triplet. These all are mentioned for single exciton, double excitons. So according to your convenience, you can use a multiple excitons. Similarly, the traps is there. If you want to define trap property, mobile ions are there where you can define the mobile ionic properties. This is mobile anion and cation. Maximum density infinite you can mention from 0 to infinite. And multiple recombination model, bulk recombinations, Auger, bimolecular simplified SRH, and with the impact ionizations. You can also even create the interface as well. Similarly, if I want to say you here, there are multiple LED structure. LED will not be there with the free tool. And this is another kind of structure where high index layer interface structure cannot possible in SCAPS or on the other tool. HTL, electron blocking layer, emissive layer, hole blocking layer, ETL, aluminum. This is one of kind of structures with master equations, SRH recombinations. Hoping model are there for interface region, and this master equation models are there. If you see, this is a master equation: singlet binding energy, triplet binding energy, and they are all related parameter for the singlet and triplet. And inter-system crossing is there. Singlet to triplet, triplet to singlet. Energetic disorder is there with dielectric constants. So triplet polaron quenching rates, mobile lines, all things, master equations, parameter are there. For single binding energy and triplet binding energy. Let me run the calculations with this master equations. Now you can see this is a reflected color, emitted color, intrinsic colors. Different color diagram and with their different current density of different materials. And different parameters are calculated. Optical, electrical, emissive, electrical, these all things can be calculated. This is extracted value and this is graphical representations. radiative decay rate, absorptance, and even the emissions. This is trap recombination model is included in this particular example. The trap model is included. Now similarly, the color will also change. Visualized color for reflected, emitter, and intrinsic, and emissive property, optical. Even I want to show you the luminance and other things. So let's run this empty data, alpha NPD, BALQ, TBPI, LIFPL, other structure. I want to take it. And here, this is device current. And this is optoelectrical property. If you want to see the luminance, this is luminance with respect to temperature. If you want to see the radiance, this is radiance characteristics. This is peak emission intensity. The combination and all those things. Now this is all about some basic things which I explore about even for LED as well. And if you will go for other kind of even perovskite LED is also possible. HAT injection is also there. Let it simulate with HATCN injection property, hoping absorption models. This is for impedance large characteristics. Left side, all examples are given in our library. Now simulation is going to complete. If you want to see this small signal analysis, FFT current initial voltage, you can see how this with respect to transient electrical segments with conductance, voltage, impedance, initial parts, real part and imaginary parts. You can see the voltage current with transient response, initial voltage. Power density and all susceptance characteristics. So I hope you have got some basic comparison as well as compared to the existing tool. You can also optimize the structures with global optimization, local optimization, global plus local optimizations. So global optimization is possible, local optimization is also possible for different LED simulations. You can optimize on different things and you can plot your characteristics on the optimization. Now, if you want to work on DSSC kind of things, then there is another module inside this SETFOS, not for DSSC, for quantum dot down conversion. So I want to tell you this down conversion scattering. This is one of down converging scattering where you can see in the middle of layer down conversion there are a lot of dots are there. This is particle. This will select the type of scattering of the layer. For me, scattering particle, quantum dot, phosphorant dye, number of ray, polydispersion, molodispersion, Gaussian dispersions. So the type of dispersion with the me theory, quantum dot, phosphorant dye kind of things, radius, concentration, some texture data can be taken, quantum yield and all those things. We want to see the absorption spectrum. This is for absorption. Analytical Kochi, Shalmier, Drude models are implemented already. This is one of interface layer where you can also enable the scattering for this particular interface. Coated interface is also possible. Coated interface where you can scattering with 3D ray tracing, micro lens array, parametrical array, cylindrical array, linear grating. So you can select type of predefined geometry for non-random seed for use of multi-threading. Cylindrical array, linear grating array. You can import your textured data as well. So BSDF textured surface data, if you want to import, it can be imported as well. And if you see, this is Gorio interface property, angular interface. You can see this 3D ray tracing data. This is 3D incident ray, scattered ray, height, R length, backup. For micro texture generation from micro lenses. Three-D ray tracing by using SETFOS. Even other H kind of property, emissive properties. Hemisphere interface is there, angular scattering, glass polarization. With different angle incoming scattering analysis. And this is scattering reflectance at particular wavelength regions. and including the spectral extractions efficiency. Normalized and all the same emission are mentioned. Even if you want to see this full OLED without surface interface. This is interface with the Pong model. So Lambatian, Pong, BSTF, Gaussian, Fourier, statistical microtexture, 3D ray tracing, root mean square RMS settings, electrical interface is there, interface scattering is there, and then multiple emitting layers is also there. So let me run the calculation for scattering full OLED simulation. Now you can see this emission. Even all this photo C-lab, trace analysis, many things are there, which I believe it could be very beneficial. Gold, organic, ALQ, calcium, bilayer interface. And this is one of LED with the two electrical interfaces there. Let me run this job. You can plot like that, different analysis. Let us see this another example for trapping large signal calculation. So this is like a transient electrical segment with frequency in hertz. Capacitance Nyquist plot can be taken, real imaginary parts. So I have tried to explain a lot of things in the short durations. Now I request to the participants if you can ask your particular query. Accordingly, I will present the remaining session demo as per your particular need or your particular interest. So now, thank you very much for listening the session. I request you can unmute your mic or you can also discuss on your chat box. And then the remaining half an hour session will be dedicatedly for you so that we can discuss on your problems. So let me go to this query session. So those who need the software, because basically the software is for limited duration. It is commercial license version tool which need to be purchased. But if you need the trial, then please you can contact to us. We can try to arrange for you. PEC is so less. No, PEC is not less. It is depend on your particular. I have taken the random parameter, but whenever you will simulate, you can get up to 35% efficiency by using the software based on different devices, Tandem or whatever you can get. So AI and ML is also trying to implement by your company. So AI and ML basically that algorithm which can be implemented in coming version, so that it can plot your more realistic data. So graded structure, I am not able to understand what graded structure. Transient solvers are there, which transient solver can solve the different equations based on that models are there, transient model. It will solve the equations. So this software does not use a DFT. Density functional theory is not implemented. It is implemented with drift diffusion one-dimensional solver. People will get the recording also. Our YouTube channel will get the recording. So the range, whatever the spectrum visible you want to use, you can define the range. I have taken the general value, but if you want to take from visible to IR, you can mention that wavelength spectrum range. Software will consider that range. So for photocatalytic application, please share me your requirement in detail. We can look into that different kind of possibility of the software, and then maybe we can try to help you or arrange some software for you. Even more information, you can visit this YouTube channel, fluxim.com, and this Fluxim YouTube channel, as well as Impulse Technology YouTube channel. This is Fluxim, our main parent company YouTube channel. You can find a lot of information that may be beneficial for the beginner. And for Impulse Technology also, you can find a lot of useful information video on our channel. This all are presented.